Okay, so we are in almost we're having some few slides. Okay, to complete this chapter means complete the switching converters. Okay, so basic ideas about switching converters. So last topic on this chapter is your switching losses. Okay, so in switching losses, here you can as you know that different solid state devices are there. Okay, so normally we are using switching converter, and for what? Actually for minimizations of these losses. Okay, so still how much sophisticated configuration you have used over here, till some of the losses will be there because of some of the energy is means you can say like that some of the charge is stored over there, then charging discharging conditions. Okay, so some of the area you have been found out, so that means switching loss area, so loss area you have been find out, so you can do the calculation. Basically it is important for our efficiency calculations of the efficiency, so that's why it is so important. Okay, for calculations of all of this. Okay, so switching loss calculations, everything. Okay, so what you have observe over here that switching losses. Okay, so energy is lost. Okay, so energy is lost during the semiconductor switching transitions. Okay, so what is a switching transition? Initially you just consider one example. Okay, just one transistor is there, one diode is there. Okay, so when transistor is switch on condition, but diode is not switch on condition, it should be switched off, because if you consider the example of a buck converter, that is coming to my next slides. Okay, so when transistor or switch is on, okay, so control switch is on, you can say like that active switch is on, and so in active switch you can use BJT, you can use any of the transistor like MOSFET, IGBT. Okay, so as per your application areas. Okay, and passive switch like your diode. Okay, so diode you may use over here. Okay, so in case of diode, then when transistor is on, means when active switch is on, then the passive switch definitely it will be off. So what will be the blocking voltage in case of passive switch? So you can say it will be started in reverse voltage. Okay, means negative voltage of your input voltage in case of buck converter. Okay, so that amount of voltage is appeared in the case of diode. So initially there will be no current through that diode. Okay, so you have considered there is that voltage amount of voltage is not responsible for reverse breakdown. Okay, so reverse breakdown of the diode. Okay, so that amount of voltage directly applied over here, but reverse breakdown is not occurred. Okay. Then when say, and the same thing you have been observed that transistor. Okay, so when it will be on, so first voltage is short circuited, then but diode voltage short circuited means switch is closed, so voltage short circuited. Then what happened? Then current, it will take some time to rise up that current. Okay, so instantaneously when suddenly that current will not be climbed up. Okay, so it will take some time to reach maximum value. Okay, so gradually it will be linearly increase up to such value. Then it will be you can say like that it is some threshold value is there. Okay, as per the circuit value, then you can say like that it is switched off. Okay, in the case of switch off, again the reversing also will happen. So it will be there is some slope. Okay, directly 90 degree, the directly 90-degree slope is not there. Some of the angular slope is there. Okay, to reach your threshold value or the set value or the design value. Okay, that climbing up your response. Okay, again the same thing also happened for the off condition, so it will take some time to climb down that all those things. Okay, so that you will find out not exactly sharp climb down and sharp climb down risk of that switch. So it will be gradually climbed up, then gradually climb down. Okay, so in between some of the area will be there. Okay, so that you have to be calculated. That's why it is written that switching transitions. Okay, in the time of switching transitions means off to on. Okay, or on to off, so the transition is there, so several mechanism also be there. Transistor switching times, diode stored energy. Okay, definitely some in terms of what the stored energy means charges are there. Okay, so charges are there means that mobility, that means that carrier. Okay, minority of the majority carrier. So normally diode is a minority carrier based control or transistor. Everything most of them are minority carrier based devices, solid state devices. Okay, so definitely that due to the charges there means definitely some of the energy will be stored over here. So how much energy is taking and how much energy is delivering means so rest of the energy, if it is still energy in between the solid state devices, that is your losses energy. Okay, means that amount of energy you are not getting back from that solid state device. So it's your loss and component. Okay. Next thing, energy stored in device capacitance and the parasitic inductances. Okay, so definitely in parasitic means what happened if you see that in case of if you go back to your measurement subjects. Okay, so in bridge circuit you can see over there in Maxwell the inductance capacitance bridge. Okay, any kinds of bridge for measurement of unknown inductance, for measurement of unknown capacitance. So you are considering one of that minimal resistance equivalent series resistance, that is called ESR. Okay, with your inductance and the capacitance. Okay, that type of resistance is called the parasitic resistances. Okay, so inherently it will present, because in ideal cases that parasitic resistance or parasitic parasitic means device capacitance or parasitic inductance is not there, but practically what I mean, it has been present over here. So due to presence of these parasitic elements, okay, so some of the additional so energy will be that means absorbed by that parasitic element. So definitely there is some losing, or that means that may cause for some the loss. Okay, means energy losses that devices. Okay, so semiconductor device are charged controlled. Okay, and the time required to, so semiconductor device are charge control. Meaning semiconductor device are working on that based on the charge, how much charge is controlled over there, dissipated over there. So time required to insert or remove the controlling charge determine the switching time. Okay, so when because it's charge control devices, so inserting and removing of that control charge, how much time is required for all the charge will be means stored over there, then dissipating over there. So that is your charge switching time. Okay, that last class it was discussed about that everything charging discharging time normally decided of your switching frequency time. If you know the switching time, so definitely you will get that switching frequency inversion of your switching time period. Okay, so you can able to observe that very basic example of a transistor switching with the clamp inductor load. Okay, so you can say like that IL is the inductor current. It's a buck converter circuit. Okay, simple circuit is there. VG is your input voltage. Physical switch means MOSFET is there, and IA is the current flow that through the MOSFET. So polarity of V is plus minus. But in case of diode, when it will be conducted, the direction of current is lower side to upper side. So you can say like it is plus, it is minus. Okay, so if you use that KVL, so it is coming Vg minus Va minus of minus Vb, so plus VB. Okay, so what is that value VB? So definitely it will come in VA minus VG. So simple thing is there. Okay, and the same thing current IA plus IB, IA plus IB, it is coming IL. Okay, so switching loss, how it is coming? So it is triangle. I'm getting over there. Okay, so what is that value? So transistor waveform is there. So you can, I think you can able to understand that transistor waveform means definitely. So initially you can get the zero. Okay, so time it is time t is there. So t0, T1 and T2. So initially what happened, it is 0 means switching time, so VA. Okay, so it is that axis is your VA. So VA means voltage appear across that switch. So initially when short circuit is, so definitely it will be 0, then automatically it will be rise up that voltage. Okay, so the voltage how up to how much? So T0 is the initial condition. Okay, at T0 value, what is that value of diode voltage? Okay, so in case of transistor, when diode voltage, how much voltage value is there? So negative Vg means you can say that Vg is definitely it will blocking voltage. Blocking voltage means negative Vg is there. Then what happened? That voltage is gradually goes to when it will be maximum. So that transistor voltage is maximum. So diode voltage will be minimum means it will be coming to the zero. So it is coming minus Vg to up to zero. Okay. So it is your VB, so climb up voltage. Okay, first climb up voltage, and when it will be then it will be same fixed up to VG. So again it will be climb up voltage. Okay, after that it will be zero. So VB will be maintained this line. Okay, again zero. So initially when the diode will be reverse bias, so we will get the zero current up to these positions. Okay, that up to this position. So we will get the maximum voltage going to be reached by that diode MOSFET up to the maximum voltage. Okay, so up to that time, so it will be current is zero because diode is reverse bias. So that voltage is there. So now voltage is zero, current also be zero. After that diode is forward bias and your MOSFET will be goes off. So how much voltage will be there? Blocking voltage will be plus VC, and up to that position that current is coming, IL current, inductor current up to that IL is there. After that it will be again rise like climb back to the zero. Okay, and maintaining zero current. So when it will be totally off, so it will take some time, T1 to T2, some time is required for total turn off for the MOSFET, and T0 to T1 time is required for total turn on of your transistor and total turn on of your diode also. Okay, so sorry, turn off of your transistor and turn on of your diode. So that amount of that area you have observed. Okay, so that area is W E effect. So how much energy will be there, energy calculation. So then what happen? It will be follow that diode current will be for rise up to IL. So it will be IL means load current or inductor current. You can say like this. So that current will be maintained overall. So if you see that up to these positions, okay, up to T1 position IL current is there. Okay, after T1 that IL that transistor current is climb down and diode current is climb up. Okay, so overall if you get that average, so average current is again it will be IL. Okay, and finally again you will get that IL value. So current is more or less constant. Okay, so there is no such changes of that current value. Okay. So what is your power calculation? So power equal to V into VAIL. Okay. So at these positions, so multiply both of them current. Okay. So multiply both of them, so you get the zero value. Okay. So at switching transition, so these positions and the switching transitions. So here you are getting that some of the values of VA, VAIG. So final one is your VG. Okay, VGIL. So that position is VA. Okay, so it is your VA. VA into how much current is there? IL current is there. So VA into IL. But what is the maximum value of VA? It is VG. That's why it is written VG into IL. Okay. After that, what happened? Same climb back to the T2, so it will climb back to the T2. So what is the area of that power loss? What is the area of that energy stored over here? Okay, so half base into height. What is your base? Okay, so base is there. So T2 minus T0, it's your base. And height, what is your height? It is Vg into IL. So half Vg into IL within bracket T2 minus T0. So transistor turn off transitions. Okay, so it is your transistor turn off transition. So I think all of you will get that calculations and get that waveform of here. Okay, so of your transistors. Okay, so for the buck converter, so it is your pulse. So DTS means up to on, then up to TS, so total time period, switching time period. It is on period, it is off period. Okay, so then the energy, the switching loss induce the transistor turn on transistors. So transitions. Okay, so energy loss during the transistor turn off transition, how much values is there? W off. Okay, so it is your W off equal to half VGIL within bracket T2 minus T0. Okay, so similar result during the transistor turn off transitions. So average power loss. So you have to calculate the average power loss. For it will be the W on means on time of your switch, so and it will be off time of your switch. So PSW means power of switching converter equal to 1 by Ts within that integral switching transitions. Okay, integral switching transition PAT into dt. So finally, if you integrate both of them, so you will get the you will get then W1 plus W1 whole into Fs. So that calculation you are getting. So you can say like this, it's an expressions, okay, not the total calculation, expression. So after that you can equate them. Okay, if you know the value of W off, so definitely W1 you are able to get. Same thing also happened for that IGBT. So IGBT, that operation is quite different. Okay, so more or less same but quite different. So two trailing is there into two way. Okay, that is called that current trailing. Okay, so current is trailing in this way. So IGBT, that current trailing is two way. That's why you are getting the two slopes over there. Okay, so first transition is there T1 to T2 first condition, then T2 to T3 because of two switches are there. IGBT is the combinations of two switches, BJT and your MOSFET. So the two switches having two different characteristics. Okay, so that's why in current trailing, okay, so two way will be there. Okay, that's why you are getting two. The rest of the things are same. Okay, rest of the things are the same. So it's your IGBT. So VA switch, VA potential voltage is appeared over here. VG is your input voltage, and you can show that voltage. Okay, so IL is your current, L is your inductor, EB is there, minus plus, and ideal diode is there. So it's your gate driver. Okay, so gate driver is there. So DT and T. Okay, DTA to TA. So it's an example of a buck converter with IGBT. So it is IGBT waveform. So similar type of your previous waveform. So IL is there, but here is current trailing is only single slope. Okay, so current trailing is only single slope. So there will be no problem. But in case of IGBT, current turning into OA. Okay, so current turning into OA, so you can get that two expressions. So IL will be there up to that position. So then IL goes down at V0. So initially it is 0 because when time down condition. Okay, in case of IGBT and diode from you are getting that it is minus VG. Okay, minus Vt is there, so then climb up to 0 value. Okay, so your current is also climb up, sorry, Va voltage is also climb up to Vg, then it will be blocking voltage, that is Vg across that, and IGBT. Okay, so current is also turn up, so up to some position, then again the current tail is there. Okay, current tail is there, so it is maximum VGIL, so you can get two of the waves. Okay, so that area is different quite here. If you combine that is compare both of the areas, so area is quite different. Okay, transistor turn off transitions. Okay, so here you will get the total expression. PSW means switching power, it will be 1 by Ts and PAT into dt. Okay, so W0 plus W off into Fs. Okay, so all are there, all the switching are there. So time logics are there, first T0, T1, T2 and finally T3. Okay, so it is your total time period. Okay, so now switching loss calculations you can go for there. Okay, so switching loss calculations means how much charging and discharging is there, so you can go for the calculations. Okay, so energy loss to the transistors for the case one. So definitely that some of the expressions are there. So WD equal to switching transitions means time period is from how much time period you are going to be calculated. That is the boundary of your integrations. Okay, so VAT, IAT. So basic equation. So abrupt recovery of the diode means definitely the transitions is there. So some of the positions, so soft recovery diode. Okay, so that is for T2 minus T1 greater than T1 minus T0. So T2 minus T1 means T2 minus T1, that is diode conduction means current is built up in the diode. Okay, and rest another is T1 minus T0, T1 minus T0. So that area you are getting, that area. Okay, that area. So that area is for soft recovery. T2 minus T1 means that area greater than T1 minus T0 minus T1 minus T0. Okay, so that area is much more. So means the slope is soft now. It is saying like the soft recovery. So the slope is here you can see abrupt slope. Okay, so abrupt slope is there, so the slope will be quite different. It is not abrupt, so area will be quite high, so it will take some time. So like that. Okay, so something like that. So if it is more compared to that, so you are getting like that, so more area is there. So it is soft, it is called soft recovery. Okay, not the abrupt recovery. But in case of abrupt recovery means how fast it will be mitigated. So how fast it will be goes to the zero. So T2 minus T1 will be less than of your T1 minus T0. Means that position, that portion is very less compared to T1 minus T0. Okay, so that is your abrupt switching, abrupt recovery time. Okay, I think I am getting that point. So with the abrupt recovery time, that VD WD equal to VG within bracket IL minus IBT into DT. So integration, all about all are that integration. Finally, you are going that the switching transitions are there, and what is that expression? So VG equal VG IL TR plus VG QR. So finally, you acquire that means calculate all of them, so you'll getting that kinds of expressions. Okay, so how much charge is stored over here. So here you can see that IA is rising up. Okay, so IA is the QR, you see that is amount of charge. Okay, that is stored over here for the transistor wavefront. This is for transistor, and diode wavefront definitely it will be there, but in reverse side. So in negative side you can get over there. Okay, so it's positive, so both of you multiply, so you will get relatively positive negative. Okay, so area is there, so that area equivalent to ILVGTR. Okay, so that area is there, QR into VG. Okay, that amount of area is there. TR is some of the time is required from this position to that width. Okay, some of the time is required. Okay, so next I told my first slide that about that some of your components are there, means parasitic components. Okay, so that inherently present over there. Okay, so due to presence of that parasitic element, so sometimes stray capacitance, stray inductance you can observe over your switching devices, and additional leakage. Okay, that's why you can say like that the device capacitance and the leakage package. Okay, so some of the leakage also be there, like that common base leakage. Okay, so in transistor analog electrons you heard about some terminology VCO. Okay, so different leakage also be there. Okay, so inherent that is that leakage current is the recombinations in the of that solid. That means carriers in between, carriers of your solid state devices. Okay, inherently it will be there. Okay, and the stay inductances are there. Okay, so what some of the features are there due to that leakage and other kinds of considerations. Okay, so here you can see that capacitance that proper effectively in the parallel with the switching elements. Okay, are stored when the switch is turned on. Definitely, so switch element I told about you capacitive component you can observe over here. Okay, means inherent, that is inherent property of the switch, because lot of doping films you are going to be used. So in between two doping film, definitely some of the capacitive activity you can observe, because of the inherently some of the stored some of the charge is stored over there. Okay, the stored energy is lost during the switch turn on transitions. Okay, so that energy is going to be lost. Okay, so switch turn on transitions, the inductance will appear. So how it will be there, inductance will appear effectively in series, with the switch elements. Okay, are open circuited and the switch turned off. So when switch is turned on, then the capacitive type of effective you can appear the parallel of your switching element. Okay, when turned on, and when switch is turned off, it is coming to the open circuited. Okay, that is property is look like your inductance. The stored energy is lost during the switch turn of transitions. Okay, so energy is going to be lost due to the switching turn of transitions. Total energy stored in a linear capacitor and inductive elements. So how much energy is going to be stored? WC you can say like that. It is half series square. You know that formula. So capacitive elements are there. So half CI VI square. Okay, And in case of inductor, so how much energy is stored over there? Half Li square. Okay, you know that formula. So half L J Ij square. Okay, so inductive element. So how much inductive element there? So summation will be there. Okay, C I means what? I equal to 1 comma 2 comma dot 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 up to n. Okay, J same thing also be there. J equal to 1 comma 2 comma dot dot up to n. Okay. So
Hello, sir.
semiconductor output
Hello, sir.
capacitance. Okay. Hello.
Sir, I have doubt.
What happened? Please tell
Sir,
me.
I have a doubt.
Tell me.
Sir, in the turn off time also there is a loss in the capacitance also, no, sir? Is it only in the previous slide, sir?
This one.
Previous slide. Ah, yes, sir.
Hmm.
Only during turn on, energy is lost in capacitance, sir. Uh, Energy is also lost in the during turn off also, no, sir? In the capacitance.
Turn on. Again, please tell me. I am not getting properly your question.
Sir, in that slide you have mentioned during turn on, energy is lost in capacitance, sir. But also during turn off, also energy also lost in the capacitance, no, sir?
Definitely. Turn off energy. No, no. Actually, in turn on condition, what it is written like that. Okay, so you just see the statement. Okay, so turn on condition, what happened? That capacitor will be like as a parallel of your switching element. Okay, that's the basic motivations. Okay, turn off time definitely it will be there. Basically, what happened? Turn off time means total voltage is already appeared over here. Okay, total voltage is already appeared to your switches, so voltage is already there, but turn on condition you are getting that what in this diagram you can see in turn on condition initially that voltage is rise up. Okay, and first sorry initially it is 0. Okay, then it will be rise up to Vg means transitions at that condition, that is actually turn on is there. Okay, so then you are going to be turned off of switching devices. Okay, so then what happen? It will take some time. Then it goes to the VG means your maximum voltage over there. Okay, so over that switch. Okay, so definitely in turn on condition you are getting more or less 0 voltage. Okay, so that's why they are saying like that, that position some of the voltage definitely it will be lost. No, some of the voltage definitely there should be the stored one. Okay, that is how to get that value. That's why in turn off condition that is getting that voltage, so it's not big problem with the turn off condition. Okay, in turn on condition, so some of the stay charge should be there. Okay, that's why they are considering that shorted. So switch elements are shorted when the switch turned on and capacity appear effectively in parallel with the switching elements. Are you getting my point? When switch is on, so it will be short circuit, so voltage will be not there. So some of the voltage means all the current is passing through that path, so definitely some of the capacity nature should be there. Okay, but by default it will be coming, by default it will be coming appear to the across the or the parallel. Okay, parallel of your switches. That's why it is saying like that. Only turn on condition it is shows the stored energy lost during the turn off transition. Okay, so that amount of energy is there. Okay, so for the turn off conditions. Okay, that's the basic reason. Okay, in case of inductance the reverse thing also happen. So if it is related to the turn on, so in turn off condition, so we are considering the inductive type property. Are you getting my point?
Yes, sir.
Okay. So here you can see that semiconductor output capacitance. Okay, so two capacitance that are that you are saying like that, CDS. Okay, drain to source. I think all of you have RD on. Okay, so RD on means RDS on. Okay, RDS on. Drain to source resistance of that in MOSFET is very important. I told you in my previous classes, because of that channel resistance depends upon your channel resistance, the efficiency of the device normally maintained. Okay, so how much current is flowing, how much resistance is there, and how much current is flowing over there. So definitely the capacity capacitive nature will be there. So it's an inherent one, that CDS, so charge DS. So due to the energy loss, the MOSFET turn on transitions. Okay, so assuming the linear capacitance, so WC equal to half C V square. So half C is your CDS. Okay, C equal to DS plus CJ. Okay, CJ means that position diode. Okay, so when the switches is turned on that condition, that CJ and CDS will be there. Okay, so that diode is there. So finally you will get that VG square. So VG is your input voltage, automatically it will be there. Okay, so in case of buck converter, you can get such examples, such type of operations. Okay, as the statement I have made, that based on that you are getting that amount of losses. Okay, so that MOSFET is non-linear. If initially you considered that it is your linear capacity, now if it is non-linear CDA, so what type of expression you will getting, that dependence of that internal CDS VDS. Okay. Yes, function of VDS equal more or less equals to C0 all under V0 by VDS. So it is directly some of the expressions I have considered. Okay, so finally you will get some of that value. Okay, so it's a root under V0 and C0. They are considering it's a C0 dash one constant like that, and root under VDS will be there. Okay, so finally will some of the expressions they have considered, and finally we will get some the final expressions for the linear capacitor. If it is energy loss is there, if linear capacitor is there, so it is that value 4 by 3 CDS VDS. Okay, function. So that kinds of thing. And if it is non-linear, so that expression is coming, that 2 by 3 CDS VDS whole into VDS square. Okay, so it's just a consideration. Okay, so to show the difference between that linear, if you are considering linear capacitance across the switch, and the non-linear capacitance. Okay, just a configuration, just a comparative study like that thing. Okay, so then another thing is there. Okay, that is not been discussed over here, but important things. Okay, so similar type of study you can do the other type of switches like those Schottky switch. So essentially no stored charge will be there. Okay, so significantly reversed by junction of the capacitance. Okay, so what are the most important features of the other devices? Okay, the transformer leakage inductance. Okay, so effective inductance in series with your winding, that you know that source inductance. Okay, so in case of any electronic circuit you are using that one, that source inductance. Okay, so that's why coming, it is your due to the isolation transformer. Okay, due to the isolation transformer and that series component you have considered in your circuit. Okay, significant loss. Okay, significant loss when that winding are not tightly coupled. Okay, so that kinds of source leakage inductance may appear. Okay, so interconnections and the package inductance also be there. So in between the diode, transistor, and the significant losses in high current application. So in several features are already there. So due to presence of that condition, some of the additional losses you can also observe. Okay, due to the inherent properties of your solid state device, maybe the connections of your isolation transformer. Okay, sometimes different interfacing. Okay, in the interference between that interference of that circuit component. So some different times may means components may arrive. Okay, due to that situation. So another thing you can observe, that is called that ringing effect. Okay, so ringing effect means what normally you can observe. Okay, in voltage and current expression, because of some of the oscillations, so when it will be turned off. Okay, means when it should be off, means here it should be off that position, but somehow it will take some of the time. Okay, for oscillations, for mitigating to the zero value. Okay, that actually that observation, so it is your minus V2 is your set value. Okay, so like your step response in your control system. Okay, so normally what happen in second order, not like only second order, it's also applicable for third order system also. So you are giving some of the value, step value, for checking your system stability, and oscillations, other kinds of thing, mean transient stability. Okay, so if you have some Planck transfer function and you will put that step value, means unit step value to your plant, so in closed loop, closed feedback path. Okay, so you will get some of the oscillation to your set value. So definitely in power electronic circuit also the same kinds of observation also be there. Okay, so how much that is also observed, because due to the that you can say like that resonance. Okay, it's like a resonance in between your LC network. Okay, resonance in between LC network. So you can see if you plot that eigenvalue, so you can see over there it will be in the positions of the eigenvalue actually may cause for oscillations of that positions. Okay, so that's the basically dynamics. Okay, dynamics of your converter. Okay, so that type of effect you can say like that is an ringing. Okay, it's written over. Okay, so induced by the direct storage charge. Okay, so charging and discharging. Okay, if you are going to be instantaneously first charging, then goes suddenly goes to the discharging mode, so normally that transition you can observe over it. Okay, so diode is forward bias while IL greater than 0, and negative inductor current removes the diode stored charge, that is your Q1. Okay, when diode becomes the reverse bias, the negative inductor current flow through that capacitor. Okay, the ringing of LC network is damped by the positive parasitic losses. Ringing energy is lost. So some of the time is required to mitigating that signal or signal to the constant value. Okay, so that is called the ringing energy loss. Definitely that energy is required. So from where it is coming, so directly it is coming in this figure that you are using silicon diode. Okay, so in this figure that diode having some stored charge. Okay, so suddenly you are going to be discharged, so it will take some time. Okay, so charging discharging in between that ringing you can observe over it. Okay, same thing also possible for basically that ringing. Here you can see that keyword. Okay, so how much loss to that keyword is T2, that position T2 to T3. Okay, that T2 to T3 minus that IL. So current is there, so that current is there. Okay, so it is your IL dt, and the energy stored in the inductor level. So definitely that energy how much stored is there. So the T2 to T3 WL equal to, so VL IL dt. Okay, that amount of energy is stored. Okay, so T2 to T3, how much inductor values during this interval, it is coming VL equal to L DIL dt. This is your minus V2. Okay, it's your minus V2. Okay, so hence WL equals to T2 up to T3 L DIL dt IL dt. So that is, you can replace those value. Finally, you will get that expression of omega equals to half L I square T3. So you can directly put this value to V into Q, V2 into QR. Okay, so it is your voltage into charge. Okay, voltage into charge, because Q I equal to Q by T. Okay, I equal to Q by T. So it is coming I equal to Q by T. So finally you will get that type of expressions. Okay, so sometimes if any kinds of loss you have to calculate, so you can go that way. Okay, so then that total efficiency versus switching losses. Okay, so how much total losses is there, so you can get from add up all the energy loss during the switching transitions. Okay, for the over the period. So you are getting W on, W off, then WD, WC, WL means loss due to the direct capacitor inductor. Okay, so switch on, switch off, all the losses are there. So average switching power loss. So after averaging all those loss, you will getting WD into Fs. So over the cycle you are going to be now. So WT by T SW. Okay, so 1 by T SW, it is coming FSW. So total power loss PSW equal to W total into FSW. Okay, so P loss equal to P conductance loss plus fixed loss plus P and the plus W total FSW. Okay, so P fixed means fixed loss is independent of load and frequency, and conductance losses due to the conductance of the switching devices. Okay, so that is your conduction losses, switching fixed losses, and the other losses also be there. Okay, so then you can plot over that figure. So how would you get that one? That if you plot them, so finally you will get that total power losses P conductor plus P fixed, so W total into FSW. So here you can get that expression. So how much if you increase that value of switching frequency, then you can observe that 10 kilohertz, that is maximum. Okay, that is more than 90%. Okay, but increasing of that switching losses, sorry, frequency, so that efficiency goes down up to 50%. Okay, here you are getting the 50%. So increasing of switching frequency, switching losses also been increasing. So that's why for high frequency operations, so you have to design some special type of switches. Okay, so that's the another motivations of these selections of the switching devices. Okay, so switching losses are equal to the other converter losses at the critical frequency. Okay, so you can say like that one frequency is, you can consider that you may say it's a critical frequency, that is P conductance plus P fixed whole divided by W total, means maximum one. Okay, so if you make that both of the losses over there, so you fix them over here. Okay, whole divided by P conductance, P losses equals to P conductance plus P fixed plus W total FSW. So if you make both of the losses equal to your W total, so how do you get that switching frequency? That is your critical one. Okay, that FSW, it should be critical one. So if P loss equals to 0, so you place them left side and whole divided by W total equals to FSW, we are getting that FSW equal to pre-critical. Okay, so it is coming from previous expression. Okay, so this can be taken, okay, this can be taken as a rough upper limit, okay, of the switching frequency of the practical converter. Okay, so if you have that all the expressions from your data sheet, so you are critically get that value of switching frequency. Okay, you are getting you can easily calculate the value of frequency. Okay, practical converter for FSW greater than F critical, the efficiency decrease rapidly with the frequency, that you can observe from the study. So selection of the switching frequency totally depends upon your critical value. Okay, so the how do you get that critical value? From your data sheet, from the fabrications, that data sheet provided by the manufacturing companies. Okay, so after getting your switching critical frequency, so you can select it is your switching frequency, because you can see at that critical frequency you can get over there that efficiency is more or less 85%. Okay, so if you plot over here, so you will get that more or less 85%. So that's the way for making it fixed. Okay, and you can see more or less it is coming nearer to the 100 kilohertz. Okay, so more or less in this device it is coming nearer to the 100 kilohertz. Okay, so that's the way to understand that how much selections of your switching frequency. So what we have studied from this chapter, so different switch studied over here. Okay, like what are the different switching devices are there. Okay, means SPST. Okay, series single point single throw idle switches. Okay, that we have already discussed. Then single quadrant switches also be there. Okay, so two quadrant switches, that is SPST. Okay, so that is also called the bidirectional voltage and bidirectional current switches. Then we discussed about synchronous rectifier. Okay, as a MOSFET connected to conduct the reverse current. Okay, that's the motivation was for the synchronous rectifier. The divide can be used for a diode with the, otherwise if we require the MOSFET is sufficient to low RD on is used to reduce the conduction loss to be obtained. Okay. Other points also be there, that majority carrier based devices, minority carrier based devices. Okay, so minority carrier based devices, you can see that BJT, IGBT and thyristor family. Okay, so high breakdown voltage are normally minority carrier based voltage, and fast switching, so like Schottky diode. Okay, so MOSFET and Schottky Schottky is the very first switching time, okay, control especially the charging of the device of the capacitance. So forward voltage drop of this device is increasing quickly and increasing breakdown voltage. Okay, so previous one that both of the case here you can see low forward voltage drop. Okay, so two type of devices are already being discussed. So energy is lost during the switching transitions due to the variety of the mechanism of the resulting average power loss. Okay, then we will discuss about the diode inductor present, then different example of the buck converter with IGBT, BJT, then current tail observed during the turn of transitions. Okay, there are other significant important significant sources like the switching losses and their effect. Okay, and their effect of their efficiency, that also been discussed. Then ringing, parasitic ringing also been discussed with the switching losses. Okay, these nine are the most significant points that are already discussed in this chapter. Okay, so we have almost covered that module 2. So module 1 and module 2 both have been completed. So in next class, okay, so we'll start with our next module. Okay, so in so